Hello, today we're going to learn about limits. Now, the good thing about limits is they're super duper easy. They're so easy, in fact, that they actually have to kind of go out of their way to try to make some tricky ones to make sure that you really do understand what they're saying. So the main thing is just to kind of not overthink what you think is the answer, because it's probably right. So there's a little bit of mathanese, some symbols that we're going to learn that's a little bit new. That's just trying to, express this idea. And the idea, again, is very simple. It's something you really already know. We've even seen it back in college algebra. So it's just a matter of learning the mathanese for what are they actually asking me. So they can ask us this question in a few different ways. They could give us an equation. They have these chart problems here where they're basically giving us the data, the numbers, and trying to get us to follow up to a conclusion. They could give us a graph and ask us to kind of analyze what's going on. Any one of these is really doing the same thing. It's saying what's going on at this point. So if they started out with just an equation like this one right here, what is the limit of x plus 5 as x goes to -1? Well, the limit as the x value approaches -1 is really, it's just going to be what is going on at an x value of -1. So I would just say, okay, well, what is -1 plus 5? And that, of course, is 4. The answer is 4. The limit as x approaches -1 of x plus 5 is 4. Just as easy as that. So this one right here, they have a fraction. Now the fractions you do need to keep an eye on because fractions are one of those things that has a rule that cannot be broken. Remember that we can never divide by 0. So you got to keep an eye on it, but always just kind of start here. Just go plug it in, see if that's going to work out for you. So let's try it here. So this is the limit as x approaches -3 of this fraction right here. So I'm just going to try it out. Say, okay, what is 2 times -3 minus 5 over -3 plus 2. Notice I put it in for all of the x's, not just one of them. So that, of course, would be -6 minus another 5 would make -11. This one is -3 plus 2 would make a -1. Negative divided by negative would become a positive 11. So this means on a graph, if you were looking at the graph of this crazy looking function here, as you reach the x value of -3, your y point on the graph would be right up here at 11. So there was no dividing by 0, nothing sneaky happened. It was all cut and dry. This one, we would have graphed a straight line x plus 5. As your x approached the value of -1, you would have the corresponding y point of 4. Now here is where they go out of their way to make it sneaky. So this one, if I started out doing the same thing, the limit as x approaches 2 of 1 over x minus 2 squared. So let's try it out just like we've done this one. So I say, draw some space here, 1 over, and I just plug it in, 2 minus 2. I say, uh-oh, that's going to make me have that 0 on the bottom, which we know is not allowed. So this is one of our special cases. So like I was saying, they have to go out of their way to make these cases that are special enough that we can see that the limit isn't always just the number, but probably 98% of the time it's just that number. So only in this lesson where they go out of their way to find these special cases do we find limits that aren't just the obvious answer. So in this case, we have a few different ways we can approach this. Depending on the problem, they might want a few different types of answers. One of the answers when this happens might just be that the limit does not exist. Okay, if you're dealing with X, Y, Z, it should tell you kind of down in the bottom in that orange box of your answer options that when you get something like this, your answer does not exist. We're going to look at some graphs too and see that sometimes these have a limit of like infinity or negative infinity. So we're going to kind of see some like that. And we're going to see some that even if you look at the graph still do not exist. So let's kind of switch over to the graph ones to make a little more sense of things like this. But for as of right now, the answer for this one is just going to be does not exist. This one on XYZ will give you an option of does not exist. So looking at the graph, whenever we have these weird cases, something like this, which might have a hole, which is something we actually learned back in college algebra. That was where we had a case that divided by 0, but if you factored it, it canceled out. So instead of making the normal asymptote, it just had a single missing value, just a hole. So something like that They also throw in some piecewise functions, which I know are nobody's favorite thing. But again, it's just they're trying to kind of emphasize these special types of limits, what's going on whenever it's not just the obvious 4. Okay, so another symbol that we're going to learn is this guy right here. So this is read as the limit as x approaches 3, not -3. See, it's just a 3. And this little symbol right here up above the 3 is a negative. So it's saying that x approaches 3 from the left. Okay, so that means if we're coming in on the 3, we're coming in from the left. Okay, as opposed to this one, this says the limit as x approaches 3 from the right. You say, well, what difference does it make? But sometimes it does. So that's where we're going to learn. So this would come into the 3 from the right. So if we were looking at the graph, here's the x value of 3, and we are coming up to it from the left, getting as close as we could to the value of 3. 3 itself has a hole, but it should appear right there at 8. The limit as x approaches 3 from the left is 8. Okay, so my equals kind of looks like a negative. Let me fix that. Equals 8. There we go. So if we came in from the right, notice same thing, it approaches that same hole, which is still there at 8. Okay, so that means the limit as x approaches 3 with no little symbol there, not specifying the left or the right, is going to be 8. It is 8 because both the left and the right came to the same value of 8, as opposed to this case right here. This one, when I approach x equals 6 from the left, notice what happens. It comes in down here at 5. So this one, if I came in from the left, it looks like the value should be right here at 5. And you may even notice there's a closed dot. We're going to talk about that as well. But if I came in approaching the value of 6 from the right, it's different. It comes up here, and right here it stops, but it looks like that value should have been at 7. Okay, so if you were like a little stick man walking along this line and it was really foggy and you were approaching the x value of 6 and you were walking through the fog, you would expect your foot to land right here on the 7. As opposed to if you were the stick man walking from the left, you would expect your foot to fall right here on the 5. Okay, since these do not match, 5 does not equal 7, this one, the limit as x approaches 6 without specifying the direction, does not exist. Since they did not meet up, there's not a single limit for the 6. They were different. It depends on which way you come. Now, again, you may have noticed the closed dot, so you might have said, oh, well, it should have just been the 5. But it's not just the value f of 6, like this right here, which in fact would have been right. The closed dot there at 5 would have been the answer. But the limit as x approaches 6, that's different. So that's how close are you getting? What would those stickmen in the fog have thought was going on? That's what does not exist. Now, what about the 3 over here where there's a hole? It looks like it should have been an 8, right? But it was an open dot. There actually was no value right there at specifically 3. So f of 3, the actual number, did not exist. Okay? So I know that's probably all clear as mud, but again, it's because it's so simple that they have to go out of their way to try to make these tricky cases. Okay, so again, try not to overthink it. You probably, without me explaining anything, if I just asked like a first grader, what's right here, what value is this, they probably would have said that it was the 8. So try to think like that. It's just what you would expect. So what if they gave it to us in a chart? It's the same idea. So we see the values here approaching 6. Okay, so it went from 5, it got closer and closer and closer and got really, really close to 6. So if I came in from the left, these are all values smaller than the 6. It got really, really close. The f of x was getting really, really close to the number 14. But what if we came in from the right, just like the stickmen here? So this one, they're getting closer and closer to 6 again. But this time, the y values got closer and closer to 15. So it's just like this case right here. There's a break, there's a gap. So coming in from the left, it should have approached 14. It was getting really close to 14. But when we came in from the right, getting close to the 6 from the bigger side, the bigger numbers, that was 15. Since 14 does not equal 15, the limit as just x approaches 6 does not exist. If they had both been the same number, then the limit would have been that number, just like the blue case over here. Okay. So these are all just distinct number answers. Now, like I mentioned over here, sometimes we deal with infinities. Okay, so let's look at an example like that. Now this one, we have two different kinds of infinities. They're both the same infinity, but it's just where we're dealing with an infinity in the x value or the y value. And we've actually seen stuff like this back in college algebra when we looked at horizontal asymptotes. So you've already had the idea of limits introduced to you. They just didn't use this symbolism, the symbols LIM x approaches, but you already had that idea. So back in college algebra, we were looking at the horizontal asymptotes, which is exactly what you see going on in this right here. So the dotted line kind of represents the fact that this pink line, which is the graph itself, comes up here and kind of levels off at this value. That's the horizontal asymptote. And in college algebra, we learned that there was 3 cases. We never did any math to find those. It was just about the degrees. Was the degree higher on the bottom, in which case we had a horizontal asymptote where the y was 0? Was the degree higher on the top, which made us have no horizontal asymptotes? Or were the degrees the same? And then we took the coefficients. So remember, since these were right here the same, that would give us a horizontal asymptote of 7/3. Okay. So going on to our limit notation, our limit language right here, same idea. This one would have a limit as x approaches infinity of 0 equals 0. This one, the limit as x goes to infinity is going to be something like infinity or negative infinity, and we're going to look at how to deal with that. So it would equal an infinity or a negative infinity. But this one, the limit as x approaches infinity, just like we dealt with this horizontal asymptote, would be that fraction 7/3. So again, no math is involved, it's just recognizing which one of the cases. Okay, so let's look at it in a graph form right here. So here I have the limit as x goes to infinity. That's the positive infinity going this direction. So we can see from the graph that it's leveling off right here at this dotted line, which has a y value of -1. What about the limit as x goes to negative infinity? Well, it happens to match up. They don't have to, but it also approaches this y value of -1. They don't have to be the same, but they are in this case. Okay, now this one you might say, well, what does this have to do with infinity? This is x approaches 2 from the left, +2 from the left. Here's +2 coming in from the left, following this pink line. Oh, it shoots up without stopping. So this is one of those cases of a limit of positive infinity. This one approaching 2 from the right. Here we go. Oh, that one shoots down to negative infinity. So that means if I just asked what was the limit at 2 without specifying left or right, that would be one of those. Does not exist because they don't match up. All right. And one more, probably a little out of order, I should have done this earlier, but jumping back to the piecewise idea, if they gave us the equation instead of the picture like this right here, we can do it that same way. The idea is just like we saw in the red and blue, do they match up? So because of that, if we deal with something like 90, which right here in the piecewise function is right inside the 0 and 100, there's no break there. There's no denominator that could be 0. It's just going to be plugging in a 90. So 11 times 90 minus 400. Punch that in your calculator, and you should get 590. Okay. A limit of 110. Well, that's over here. So again, that's not right on the edge. Nothing's breaking there. There's not any denominator that might be a 0. So I'm just going to punch in 110 into the bottom one because 110 is between 100 and 250. So it's going to go 11 times 110 minus 225. 225 because it's the bottom one. Punch that in your calculator and you should get 985. Easy peasy. Okay, but what about 100 itself? Well, 100 is tricky because that's where it breaks. You might say, oh, well, just be this one because that one has the closed dot, the bar. But again, it's just like this guy right here. Even though we had the closed dot, yes, f of 6 would have been that value. We're not asking what is f of 6. We're saying what is the limit. So are they going to meet up going from the left and going from the right? So really right here, I have to ask myself, what is the limit as x approaches that 100 from the left, and then what is it as it approaches the 100 from the right? Are they different? So I have to know both of them. So from the left, I'd plug it into the top, so that would be 11 times 100 minus the 400. But from the right, it would be the 11 times 100 minus the 225. And you can probably guess that they're not going to be the same. So the 400 gives us 700, but the 225 gives us 875. Those, of course, are not equal. So that means the limit as x approaches 100 without specifying a direction does not exist. There is no other way to do that other than plugging it into both. We needed to know if the left and the right matched up, and they did not. Okay. All right, so on this problem right here, I said that it might have been infinity or negative infinity. But we have to kind of test that out. So we're going to look at some examples like that. Most of the time, the easiest way to do something like that is to go ahead and plug it in your calculator and see, was it doing something like this? Was it just going up to infinity? Was it going down to negative infinity? Usually it's pretty obvious. So let's look at some like that and some of our special cases here. So on this one, again, I always kind of start with plugging it in just to see what numbers are going on. But right away, I see when I'm plugging this into the denominator, it's that special case, excuse me, where it's going to make a 0 in the denominator. That's not allowed. So it's going to be one of our special ones. So to see if maybe, it's weird. Okay, to see if maybe it's this case where it's just a whole, but it does still have a limit. The easiest way to check that is to factor. Now, if you've used my programs in college algebra before, there's actually a program for factoring trinomials. So if you have that, a reminder, you would go to your calculator, hit the program button, which is the third one down here in the middle, and scroll down to the program factor. Okay. And then you select it, hit enter to run it, and then it's going to ask for the A, B, and C. So my A in this problem would be 1, enter. My B would be -5, enter. Make sure you're using the little negative, -5, enter. And then C is 4, enter. And then it gives you the factored binomial. Okay, if you don't have that on your calculator, or maybe if you're just more comfortable factoring by hand, that is fine. This one is a pretty easy factor by hand because the only thing that multiply to 4 is 1 and 4, or 2 and 2. And the one that would make a 5 would, of course, be the 1 and 4. But to make it a negative, they would both need to be negatives. And that's lucky because now we have that matching x minus 4. So I can see that they would have canceled out. Now, like we learned in college algebra, even though it cancels, we still can't use the value 4. It would still make us divide by 0. But basically, it shows us that this equation reacts just like the limit as x approaches 4 of just x minus 1. Oh, sorry. 1. The one that didn't cancel here. So if you graph this in your calculator, it would look exactly like graphing the line x minus 1, except it would have a little hole right there at 4. So now that it's factored out, I can just plug that in, 4 minus 1, which is, of course, 3. Okay. Screwed him up. All right. Now this one, we can see again, I could try to plug it in, but when I plug this into the denominator, oh, it's going to give me that 0 in the denominator. So if I try to factor it, you could use that factor program in your calculator, and you punch in the 1, the -2, and the 8, and it does not factor. If you were trying to do it by hand, you'd say, okay, well, the only things that factor to 8 are 1 and 8, or 2 and 4, and you say, oh, well, 2 and 4, that should work. It seems like it should be x minus 4 and x plus 2, because that would make the -2 in the middle, but -4 times +2 would make a -8. So it's not that. It doesn't actually factor. So right away, I can see that this is not going to work out. I can't factor, and even if I did, I definitely wouldn't have a factor of x minus 1. So this is going to be one of those harder ones. It does not factor. It's not going to leave just an empty hole. It's going to be something broken or a go up and down to infinity. Okay, so on XYZ, again, it will specify. It probably just wants a DNE. Okay, because it doesn't factor. But real quick, let's just look at the graph of it. So if I type that into my y equals, make sure to use parentheses. So parentheses x squared minus 2x plus 8, close the parentheses, divided by parentheses x plus 1. And you can see what's going on. Why can't we get a value there at -1? Okay. Let me double check. Yeah. So here is my graph, and -1 is back here. You can see something's going on. In fact, let me zoom out. Now we can see it a little better right there. So it's a lot like this case that we saw right here, where one side of it shot up and one side of it shot down. As you can see right there at the -1, it was the asymptotes that shot up and down. So that's why even if we looked at the graph, one side, x approaches -1 from the left, would equal -infinity, but x approaches -1 from the right would equal +infinity. So it still does not exist. Okay, so I didn't really have to look at my calculator for that. I could just see when it didn't factor that it didn't exist, but you can always kind of double check. All right, now this is the sneakiest one. There's this little trick in here. So this is something that we don't usually do in math. It's something that's kind of special for limits. In college algebra, you've learned how to rationalize the denominator, because there was that weird rule that you cannot have square roots in the denominator. But in this problem, we actually end up rationalizing the numerator, and it's not a math rule. It's just an interesting trick that makes this specific type of problem work out. So if I tried to plug in a 9, of course, it's going to make the 0 on the bottom, and you could kind of factor if you think of it that way, but here's what they generally show you in the help videos. Okay, so just like we learned rationalizing the denominators back in college algebra, we're going to do that for the top. So I use the same square root of x, the same 3. Oops. But the opposite sign. This one had a minus, so I'm going to do a plus. Okay. So right here, I FOIL this out. So I go square root of x times square root of x is x. Square root of x times 3 would be a +3 square root of x. This would be -3 square root of x. 3 times 3 would be 9. Positive times negative is negative. Okay, on the bottom, I know this looks weird, but just go with it. X times square root of x is x square root of x. X times 3 would be +3x. -9 times square root of x would be -9 square root of x. And -9 times +3 would be -27. Okay, I know it looks weird, especially this right here. We don't see very often, but this is all going to magically work out. It's kind of cool. So these, of course, cancel out, positive and negative. So we're left with just an x minus 9 on the top. On the bottom, really none of these they're not like terms, they cannot combine. So I'm just going to leave this whole thing. But here's the cool thing, it's all going to work out. It looks like a mess. All right. So technically I was being a bad mathematician right here because I wasn't putting in my limit. Try to correct that right here. Okay, so technically I shouldn't have just put equal, it was that the limit was equal. Okay, all right. So before I could not put in a 9 because it made me get a 0 on the bottom, but watch what happens now. Now I should be able to. So I get 9 minus 9 on the top. Wait, hang on a sec. Nope, sorry. Okay, backtrack. Okay, got excited. Okay, sorry about that. Hope you're not writing in pen, but if you are, just write underneath it. Just scribble that part out. So I got excited. Wanted to foil, but actually leave this part unfoiled and it's going to work even better. Okay, sorry, because now we get that x minus 9 on the top, just like we had. But when I leave it factored, instead of foiling that big mess together, here's where the trick is. You don't do this trick very often, so I forgot where I was going. Okay. So now notice it matches up. So I have this matching x minus 9, so it factors out into the limit as just 1 over square root of x plus 3. Okay, so when that canceled out, we're left with this, which still looks like it should be a problem, but let's try plugging it in. So if I go 1 over square root of 9 plus 3, square root of 9 is, of course, 3. So I end up with the fraction 1/6. So if you graph this out, again, there would be a hole right there at 9, but if you came in from the left or the right, it would go right up to that fraction of 1/6. So something super duper close to 9, like 8.999 or 9.001, both are going to give you answers really, really close to 1/6. There's just a hole there. So again, this isn't a trick you use very often. It mostly comes up in calculus problems, kind of like this. This is called rationalizing the numerator. So it's not because it's mathematically required like it was for rationalizing the denominator. It's just that it happens to do this for us right here. So if you kind of find yourself stuck, try something like that. Okay, so that's all for this lesson. Let me know anytime you have questions.